The title of my presentation is Dugdale Model for Plastic Zone Size of Contracting Cracks on the Plane Deformation. And geometers will present the geometry of the problem. Suppose we have an isotropic plastic layer weakened by some cracks. The cracks can be, for example, a horizontal crack or vertical crack or inclined crack. And you can see we have a layer with thickness h. We want to specify the shape of plastic zone, the size of plastic zone ahead of the crack tips, but we want to specify it on the crack line. We will use the Dugdale's model to specify this size of the crack zone. Steps, definition of the problem, formulation, numerical result, and conclusion. We will use the distributed dislocation technique, and this is a very efficient technique. And this technique has some advantages, such as possibility of consideration of multiple cracks and the possibility of consideration of interaction between the cracks. First, we will find the screw dislocation solution using the image method. Then we will construct some integral equation using the dislocation solution. And by solving these integral equations, we will find the solution for crack problem. And finally, based on the Dugdale's model, we estimate the plastic zone size ahead of the crack. And suppose, again, this is the geometry of the problem. This is a layer with thickness h, and we have a screw dislocation at point S. This is the point S. And we consider a screw dislocation with magnitude of Berger's vector dz. This is the displacement field for out-of-plane, anti-plane displacement. And we extracted this solution from this reference, and it has been extracted, has been drawn using the image method. We will use this solution. This is the constitutive equations for anti-plane deformation. By substituting the displacement into these equations, we will find the stress components. It's easy to show that the stress component satisfies the traction-free condition on the lower and upper, here and here. These edges and this edge and this edge are stress-free, and it's easy to see this solution satisfy this condition. Also, it is easy to show that the stress components has a Cauchy singularity at the dislocation and location. And we distribute some dislocation on the borders of the cracks, and we construct some integral equation you can see here. And this is the dislocation density, and the kernels can be found using the previous stress components. The left side of the equation can be found using the Wagner's principle, and this is resulting from the external load. You can see here, this is the stress components coming from external loading. The external loading can be applied on the lower or upper edges of the layer. According to Dugdale models, we have a physical crack from here until here, and we have another extended crack from here until here. The new tips of the extended crack are not singular, and we will apply the regularity of the stress components at these tips. This one and this one. And this is the left side of equation by considering the Dugdale models. We will consider the yield shear stress at the plastic zone ahead of the crack tip, on the crack tips. And by specifying the CI and DI, you can see in the left, in the previous figure. By finding the CI and DI, we can estimate the size of plastic zoom. And this is the left side of the equation. We will solve the integral equation. After finding the BZ here, by introducing this change of variable, we can find GZ and we can find the stress intensity factor for embedded cracks. And by applying the regularity of the stress in new tips, I mean the tips of the extended crack, I mean these relation, we can solve the integral equation numerically. We will discretize the equation at these discrete points, and finally we solve the problem, and we will find the CI and DI, and we will specify the size of plastic zoom. And to validate the work, we introduce an infinite plane with crack, and this is the integral equation. By analytical solution of the integral equation and using the change of variable, after doing some lengthy calculation, we will find the following solution. And by applying the condition for the regularity of the stress field on the tips of new cracks, we will find this relation. This is the C is the size of cracks, size of plastic zone, and you know this is a very well-known solution. You can find it from this reference. This is the solution, but this solution has been found using the complex variable method. We will find it for infinite plane, but we want to tell that it is we can generalize it for the layer, I mean our problem. And we will furnish the paper with some example. In the first example, we consider a central crack with perpendicular to the boundaries of a layer, and we will present the size of plastic zone in terms of different loading ratio. You can see by increasing the loading ratio, the size of plastic zone is increased. Also, we will present another example. In this example, we consider a central parallel crack to the boundaries of the layer, and again, you can see here, this is the size of plastic zone in terms of the loading ratio for different crack sizes. In the final example, we will apply the method for two crack parallel to the boundary of the layer, and you can see the size of plastic zone for different loading ratio. For two adjacent tips of the crack, because of the interaction of these tips, you can see the size of plastic zone is bigger than other tips. So finally, we conclude that the distributed dislocation technique is an efficient method to analyze the crack problems, and you can apply the Dugdale's model, and you can specify the size of plastic zone ahead of the crack, but only in the crack line, because it is the limitation coming from the Dugdale's model. And it's applicable to every interacting cracks, and you know the size of plastic zone has a very crucial, and I mean it's very important for fracture analysis. And finally, thank you for your attention.